Welcome back to the deep dive. Today we're tackling something absolutely fundamental, the language of organic chemistry. And we're going to use its own rules to decode the architecture of life itself. We're diving into this really complex system that lets us name and understand pretty much every carbon compound out there, from, simple gases to the proteins inside your own body.
Right.
Our sources for this are the bedrock of the field. We're talking the definitive IUPAC guides, some foundational review materials on molecular structure and biochemistry.
And our mission here, I think, is really important.
It is. We aren't just here to recite rules. We're finding the reasons these rules exist, the shortcuts for predicting structure, and, I think most importantly, the surprising exceptions that actually dictate how biology works.
And that's everything, really. The nomenclature, the language, it can sound so academic, but you just can't do modern science without it.
It's non-negotiable.
Completely. If you try to talk about a chemical structure without these precise, agreed-upon rules from IUPAC, you just get ambiguity. And that's not just, a problem for a student.
No, it's a real-world problem.
It's a huge problem. You're talking about disrupting global supply chains, failing drug safety trials. At the end of the day, without this common alphabet, chemistry and industry just wouldn't function.
Okay, so let's unpack this universal language. I want to start with the core philosophy of it all. It's built on something called substitutive nomenclature. What does that actually mean?
It's a really elegant way of thinking about complexity. Instead of naming every single atom, you look at a molecule as having two main parts.
Okay.
You've got a core structure, which we call the parent compound. That's usually the longest carbon chain or central ring system. And then you have all the other pieces attached to it, which we call functional groups. The whole systematic name is built around that parent.
So the parent is the backbone, and the functional groups are like accessories attached to it.
That's a great way to put it.
Then why do we need this other concept, the preferred IUPAC name? The PIN-in. I mean, chemists use common names like styrene for decades. Why the push for a single preferred name?
It all comes down to ambiguity, which can lead to, frankly, regulatory disaster. You mentioned styrene. Its systematic name is ethynyl benzene.
Right.
But even under the old rules, there might be a couple of valid IUPAC names for it.
Yeah.
And in a regulatory context, for shipping, for safety, for pharmaceuticals, you cannot have ambiguity.
You need one name.
You need one name. The Blue Book, which is the guide, it provides a very strict set of rules, a hierarchy, to select one and only one, PIN-in. It's specifically for legal and regulatory documents to remove any chance of confusion.
That makes it sound a bit bureaucratic, but I can see why it's absolutely necessary.
Oh, it is.
So let's walk through the steps of building a name, just to show everyone how logical this language really is. It's a very orderly process.
It is. The logic follows a priority list. So
Right.
First thing you do is find the parent structure, longest chain, or the most senior ring.
And step 2 is the big one, right? This kind of determines the molecule's whole identity.
Exactly. You then have to identify the single principal characteristic group. This one group is so important that it actually dictates the suffix of the name.
So if it has a carboxylic acid group,
Then the name will end in oleic acid. And that group takes priority over, say, an alcohol group that might also be on the molecule.
so there's a seniority, a molecular hierarchy.
There is. After you've picked that principal group, you assign locants, which is just a fancy word for numbers.
The address on the chain.
Precisely. It's the numerical address that tells you exactly where everything is attached. And you number the chain to give that principal group the lowest possible number.
The most important group gets the best address.
You got it. Once that's all set, everything else, all the other functional groups, they just get listed as prefixes, and you put them in alphabetical order.
And finally, the 3D part.
Yes. Finally, you add what are called stereodescriptors, your R's and S's for chiral centers, or ES and Z's for double bonds, to describe the exact three-dimensional geometry.
Okay, so give us a quick lineup of that hierarchy. Who's the CEO that always gets the suffix?
The carboxylic acids.
Wow.
They're absolutely the CEO. They're the most senior. Then you have their derivatives like esters. Then you get into groups like aldehydes and ketones.
Suffixes like -al or -one.
Right. And below them are alcohols with the suffix -ol or the prefix hydroxy. And then further down, you have things like amines. This strict ranking just ensures that no matter how complex the molecule is, it only has one possible principal group,
And therefore, one unique PIM.
one unique PI.
All right, let's shift from the abstract language to the physical architecture. If naming is about communication, then geometry is really the blueprint for how these things react. We use concepts like VSEPR theory to get these standard shapes, tetrahedral, trigonal planar, linear. But the fast way to do that is determining the hybridization. OSPI, STTI, SPIs, EFPI. Is there a reliable shortcut for that?
Oh, there's a beautifully effective shortcut. It saves so much time. For any central atom, you just count two things: the number of atoms attached to it plus the number of lone pairs on it.
Okay, so the sum tells you everything.
The sum tells you the hybridization. If the sum is 4, it's PBOE. 3, it's dirt PUC. 2, it's PPO. Simple as that.
That seems almost too easy. But for people looking at these skeletal line diagrams, where they hide the hydrogens and lone pairs, how do you use the shortcut correctly?
That's the key. You have to assume a full octet, 8 valence electrons, for your common atoms like carbon, nitrogen, oxygen, and fluorine. Always assume the octet is full, even if the lone pairs aren't drawn.
And there's one exception to that.
There's one big exception. A carbon atom with a positive formal charge of carbocation. That only has 6 electrons. But for nitrogen and oxygen, you always assume they have their full octet.
Okay, so here's where we get to the real insight. Just when you think you have a rule that works, organic chemistry gives you an exception that isn't a glitch. It's actually the engine that powers biology.
Right.
Tell us about the main exception to this hybridization shortcut.
So the major exception happens when you have an atom with a lone pair, and it's positioned right adjacent to a pi bond. Think of a nitrogen atom right next to a carbon-oxygen double bond.
Okay, so our shortcut would say 3 attached atoms plus 1 lone pair, so that's 4. It should be SPORM. Pyramidal.
It should be.
Mm-hmm.
But in reality, it's not. It adopts Synsporn hybridization. It becomes planar.
Why? Why would it do that?
It's because that lone pair on the nitrogen, it prefers to sit in an unhybridized orbital rather than an Olin-spornable.
And by doing that,
it can align itself with the orbitals of the adjacent pi system. It allows the lone pair to overlap with them. And this is a mechanism we call conjugation, or resonance.
So the molecule gains more stability by spreading those electrons out through conjugation than it loses from the increased electron repulsion of being planar.
Precisely. You gain more stability through delocalization than you lose from localized crowding. There's an energetic trade-off. And that tiny energetic preference, it's only about 10 kilocalories per mole. That's the structural key to life.
And the prime example of this is the amide, the bond in proteins.
Exactly. The nitrogen in an amide is planar, spigot side, not pyramidal like in a normal emi. And that planarity creates rigidity.
Because that CN bond is no longer just a single bond.
Right. Because that nitrogen lone pair is delocalized through conjugation, the CN bond takes on significant partial double bond character.
Yeah.
It can't freely rotate anymore.
And that's been proven.
Oh, yeah. X-ray crystallography confirms it's planar. And that rigidity is the physical constraint that forces a long polypeptide chain to fold into specific functional shapes, like alpha helices and beta sheets. Without this one little exception to our shortcut, proteins would just be floppy, useless messes.
That's a perfect bridge. A tiny optimization in orbital mechanics dictates the entire macrostructure of the body. So let's expand on that. We mentioned amino acids.
Right, the building blocks. Amino acids are fascinating because they're amphoteric,
Which means
it just means they have both an acidic part, the carboxyl group, and a basic part, the amino group, so they can act as both an acid and a base. This lets them exist as zwitterions, these internal salts, at physiological pH, which makes them really versatile.
And it's also amazing how life is so picky about which mirror image it uses. We talked about handedness, stereodescriptors. Biology doesn't leave it to chance.
No, it's highly, highly regulated. It's one of the great mysteries. I mean, think about it. Nearly all natural carbohydrates, the sugars that fuel us, are D-sugars. But nearly all amino acids that make up our proteins are L-amino acids.
There's a fundamental bias built right into the machinery of life.
A huge bias. Our enzymes are designed to fit one specific enantiomer. It's like they're built for a right-handed glove, and a left-handed glove just won't work.
Except for cysteine, the famous exception.
Right. Cysteine is still an L-amino acid, biologically speaking, but because of the sulfur in its side chain, the naming rules, the priority rules, assign it the stereochemistry. It's a fun little quirk of the system.
Okay, let's jump to a totally different structure. The cell membrane. We describe it with the fluid mosaic model. It's dynamic, sort of semi-solid. How does something like cholesterol regulate that entire structure?
Cholesterol is a steroid, and if you look at its structure, you see these 4 rigid fused carbon rings. That rigidity is its superpower.
How so?
Well, the membrane is mostly made of phospholipids, with these long, flexible fatty acid tails. And when it gets cold, those tails want to pack together really tightly which would make the membrane stiff and brittle.
So cholesterol gets in the way.
It literally gets in the way. It inserts itself between those tails, and because it's so rigid, it acts like a spacer. At low temperatures, it prevents the packing, which increases the fluidity.
And at high temperatures?
It does the opposite. At high temperatures, the membrane could get too loose, too fluid. But the rigid steroid structure of cholesterol helps to stabilize it, holding it together and decreasing the fluidity. It's a brilliant little temperature buffer.
So its chemical geometry, those fused rings, is what lets it control the mechanical properties of the whole cell.
Exactly. It's the structural anchor in a very fluid world.
Last one, the ultimate information systems. DNA versus RNA. They're built from very similar blocks, yet one is the stable vault and the other is just a temporary message. What's the chemical difference?
The difference is a single hydroxyl group. One oxygen atom.
That's it.
That's it. RNA uses a sugar called ribose, which has a hydroxyl group on the 2' carbon. DNA uses deoxyribose, which, as the name implies, is missing that oxygen. Deoxy.
And that one hydroxyl group makes all the difference.
All the difference. That extra OH group in RNA makes the whole molecule chemically less stable. It's much more susceptible to breaking down through hydrolysis.
Which explains why messenger RNA is so short-lived.
It's designed to be ephemeral. It delivers its message and then degrades. DNA, because it lacks that reactive group, is built for the long haul, and the machinery reinforces this. DNA polymerase has proofreading mechanisms to ensure high-fidelity replication. RNA transcription, not so much.
You want accuracy for the blueprint, but speed and turnover for the memo.
That's a perfect way to think about it.
So, after all this, what does it all mean? We've gone from the regulatory need for a preferred IUPAC name all the way to the predictive power of a hybridization shortcut. But I think the real insight was in the exceptions. That exception, the planarity from lone pair conjugation, isn't some mistake in the rules. It's the fundamental compromise that creates functional biology. It's what makes the CN bond in every single one of your proteins rigid.
It really is a spectacular example of quantum mechanics setting the rules for life. That tiny energetic nudge, just 10 kilocalories per mole, that forces an amide nitrogen to be planar. That is the reason proteins can fold into the specific shapes they need to function. If that bond could just spin freely, life as we know it would collapse into chaos.
A micro-level optimization dictating the entire macro world.
That's what chemistry is.
It's just incredible. So considering that the planar nature of that peptide bond is so critical for protein folding, it leaves you with the question. What other seemingly simple, maybe overlooked chemical geometry shifts? A subtle bond angle, a preferred hydrogen bond, might be regulating huge biological systems right now without us even realizing their full importance. Something to think about. Thanks for diving in with us.